So, we've looked at the two main vector operations of addition and scaling by a number. And those are all the things we really need to be able to do to define what we mean by a vector, the mathematical properties a vector has. Now, we can move on to define two things. The length of a vector, also called its size, and the dot product of a vector, also called its inner, scalar or projection product. The dot product is this huge and amazing concept in linear algebra with huge numbers of implications, and we'll only be able to touch on a few parts of it here, but enjoy. It's one of the most beautiful parts of linear algebra. So, when we defined a vector initially, this guy R, we did it without reference to any coordinate system. In fact, as a geometric object, this thing just has two properties. Its length here and its direction, which is going this way, as opposed to this way or this way. So irrespective of the coordinate system we decided to use, we want to know how to calculate those two properties, its length and the direction it's going in. Now if the coordinate system that we use to define R used these two vectors I and j, we can say that R is equal to AI plus BJ, or is equal to AB, the way we were writing it in the last video. Now, if we want to know the length of R, well, we can draw a triangle, right? And then we can use Pythagoras' theorem. So we've got AI's going along this way, and we've got BJ's going along this way. And if I and J are both of unit length, that is, the length of those is just A here and B here, where this vertical lines on either side means the size. So then we can use Pythagoras' theorem just for a triangle, where we've got A there, B there. This length then, from Pythagoras' theorem, will be the square root of a squared plus b squared. And we can say that that's equal to the length of R. It's the square root of a squared plus b squared. So the length of R is equal to AB. So R is that. And the length of R we define to be equal to the square root of a squared plus b squared. Now, we've done this for two spatial directions defined by the unit vectors I and j, and those are at right angles to each other. But this definition of the size of a vector is more general than that. It doesn't matter if the different components of the vector are dimensions in space, or even things with different physical units like bedrooms and bathrooms, or length and time and price. We still define the size of a vector through the sums of the squares of its components, all square rooted. The next thing we're going to do is define the dot product, which is one way of several, of multiplying two vectors together. So we've got two vectors here, R and S. And I'm going to make this a bit more general actually. I'm going to give them components. So I'm going to call it Ri, Rj. So R has a component I, in this case 3, and a component j, in this case 2, in the j directions and the I directions, respectively. And S, we can do the same thing. We can say S has components Si and Sj. So then we define the dot product, and the dot product is just a number, like 3. It doesn't have any associated spatial dimension or direction along the vectors I and j. We'll define the dot product R dot S to be equal to what happens if I multiply Ri by Si and add it to Rj times Sj. So in this case, that gives me, it gives me 3 there times minus 1 plus 2 times 2. So that gives me 3 plus 4, minus 3 plus 4, which is equal to 1. So the dot product of R plus dot S in this case is minus 3 plus 4, which is 1. Now, we can go on to look at one property of the dot product, which is that it's commutative. So commutative, which is spelt commutative. And that means that R dot S is equal to S dot R. It doesn't matter which way round we do it. And we can see that fairly simply, because if we just switch that around, we'd have Si times Ri plus Sj times Rj, and that's going to be the same number. So we can see immediately, fairly trivially, that the dot product is commutative. It doesn't matter which order we do it in. Now the second property we're going to prove is that the dot product is distributive over addition. So if I have some third vector, let's take some third vector t, what being distributive means is that r dot s plus t is the same as r dot s plus r dot t. That is, we can multiply out this bracket in the way that we would if they were just numbers. And we're going to prove this in a general case for any dimension vectors. So we'll have a vector r is equal to components r1, r2 for i's and j's all the way up to some dimension rn. And s is some other vector s1, s2 all the way up to some bit sn. And t is another one which is equal to t1, t2 all the way up to some component tn. And then r dot s plus t is going to be equal to r1 times s1 plus t1 plus r2 for the second dimension times s2 plus t2 plus all the other dimensions plus rn times sn plus tn, if I multiply it out for all the dimensions. And then I can just multiply out those brackets. That's going to be r1 s1 plus r1 t1 plus, now multiply out this bracket, r2 s2 plus r2 t2 plus all the dots, rn sn plus rn tn. And if I collect together the rs terms, I've got r1 s1, r2 s2 and rn sn, so that's r dot s. And if I collect all the t terms together, I've got r dot t. So we've demonstrated that this distributive property is in fact true. So it's also kind of obvious that if we multiply a vector through by a scalar, so if we take a times s, that's our other fundamental operation was multiplying by a scalar, and then do the dot product on that, so we do r dot as, then that's going to be equal to a times r dot s. Because if we take this s here, when we do this, if we multiply s here through by a number a, we're just going to get the number a come out of all the components. So that's going to be, if we do it, ri times a si plus rj times a sj. That's the left-hand side. And that's equal to a times ri si plus rj sj. So that is, this property is called that it's associative over scalar multiplication. Over scalar, that's the number a, multiplication. So we've got three properties. We've got it's associative over scalar multiplication, the dot product is distributive, and it's commutative. Now the last thing we need to do is draw the link between the dot product and the size of the vector. This is quite surprising. If we take r and dot it with itself, we get ri times ri plus rj times rj plus all the other components, whatever they are. So that's equal to ri squared plus rj squared. But we said that the size of the vector was the square root of that. So r dot r is equal to the size of the vector squared. So that is, the size of the vector is just given, in some senses, by r dotted with itself, which is quite cool.